Hello, everyone. So, my name is Hamza Zakia, and today I will be presenting a research work titled Software Runtime Monitoring with Adaptive Sampling Rate to Collect Representative Samples of Execution Traces. This presentation discusses how runtime monitoring systems can collect meaningful execution traces while keeping the performance overhead under control, especially in environments with variable workloads. So, in the introduction, runtime monitoring plays a critical role in modern software systems. It allows developers and operators to observe system behavior during execution for purposes such as debugging and verification and performance analysis. One of the most common monitoring techniques is collecting the execution traces, but however, while execution traces are highly informative, collecting them at scale introduces runtime overhead and operational cost. This challenge becomes more severe in systems where workloads are dynamic. The research presented here investigates an adaptive sampling approach that aims to preserve the representativeness of execution traces while actually maintaining acceptable system performance. So, for slide 3, which is background and motivation, so in recent years, cloud-based and microservice-oriented systems have become the dominant architecture. These systems generate extremely large volumes of execution traces due to the high request rates and service interactions. To manage this volume, sampling is widely used, but however, recent studies show that poorly designed sampling strategies can distort the uh, distort the observed system behavior. The distortion reduces the reliability of runtime analysis, unfortunately, and makes diagnosis more difficult, particularly under dynamic workloads and frequent traffic spikes. So, for research, for the slide 4, which is research problem, the most existing runtime monitoring solutions rely on fixed rate sampling or simple adaptive heuristics. While these methods reduce monitoring overhead, they struggle to handle workload variability. During traffic spikes, system behavior can change rapidly, yet these sampling strategies may either oversample, causing performance degradation, or undersample, leading to biased and unrepresentative data. As a result, the collected execution traces may fail to reflect the true behavior of the system, limiting the effectiveness of monitoring and performance analysis. So here we finished slide 4. Let's go to slide 5 and go a little bit down, making it more comfortable. Okay, so slide 5 talks about the research gap. Although recent adaptive sampling techniques have improved efficiency, many of them focus primarily on cost reduction. They do not explicitly ensure that the collected samples remain representative of the underlying execution behavior. In particular, throughput-based adaptations can introduce sampling bias during critical periods. The key research gap addressed in this work is the lack of runtime sampling approaches that dynamically adapt while validating representativeness using statistically grounded criteria. So, for slide 6, the proposed approach. To address this gap, the paper proposes an adaptive runtime sampling process that treats representativeness as a primary objective, and instead of just adjusting the sampling rate solely based on workload, the approach actually evaluates sample quality during runtime. So the first sampling decision is made for each request actually. And it is a process that and but the process is consisting of three main activities, which is I just said the first one. And the second one, the sampling rate is adapted dynamically during a monitoring cycle. The third one is sample evaluation, performing to assess whether the collected traces remain representative or not. This design allows the system to balance performance, overhead, and data quality to be more effective. So for slide 7, methodology and experimental setup. So the proposed approach is implemented and evaluated using 5 benchmark applications. It is compared against 2 baseline strategies, uh, which is uniform sampling and inverse throughput sampling. The experiments are conducted under both stable workloads and workload spike scenarios. This experimental setup enables a controlled evaluation of how the adaptive approach impacts runtime overhead and sampling accuracy under realistic operating conditions. And for slide 8, we have the results. The experimental results demonstrate that the adaptive sampling approach significantly improves the representativeness of execution traces, especially sampling error. It is measured using root mean square error, and it is reduced by 9 to 54% compared to inverse throughput sampling. At the same time, the runtime overhead remains limited, increasing by only 1 to 6%, as you can see, relative to the baseline. These results show that the improved quality can be achieved without substantial performance penalty. So now we hit to the slide 9 and let's go down a little bit. Okay, so in slide 9, the discussion. So these findings indicate that improving representativeness does not require this disproportionate increase in monitoring overhead. The proposed approach achieves a more reliable balance between accuracy and performance. So this is particularly important in real-world systems where biased monitoring data can lead actually to incorrect operational decisions. The results are also consistent with recent trends in distributed tracing research, which actually emphasizes adaptive and state-aware sampling strategies. And for slide 10, conclusion and future work. So, in conclusion, this work presents an adaptive sampling approach for runtime monitoring that improves the representativeness of execution traces while maintaining acceptable system performance. By explicitly evaluating sample quality during runtime, the approach addresses a key limitation of existing monitoring strategies as future work. The approach can be extended to distributed and cloud-based environments where workload variability and network effects and large-scale tracing introduce additional challenges, such as extensions, like it would further strengthen the practical applicability of adaptive sampling in modern observability systems. And in slide 10, we have the references. As you can see, the oldest references that I have in my research paper is from 2022. And that's it. I hope you enjoyed the presentation and thank you for your time.